Good evening, everyone. Myself Sana Sheikh, a PhD student from IIT Bombay, and I'm a TA of your course, NPTEL course, that is Symmetry, Stereochemistry and Applications. The course instructor is Professor Anshuman Roy Chaudhary from ISL Mohali. Every week from 7 to 9 p.m., I'm taking your live session, which is based on previous year questions of this course, and we are discussing those questions assignment here. So this is a week 3 live session. In this live session, we are going to discuss about the conformation, configuration, and stability of the organic molecules. So let's start the session. This is the question number 1. Draw the energy profile diagram of the molecule given and below using the C-C bond as a axis of molecule. So as we have discussed in previous lecture, we have discussed the Newman projection of this type of molecule. So how will you draw Newman projection? First of all, we should know how to draw the Newman projection of these molecules. Then we will discuss the energy profile diagram. So if I will draw the Newman projection by considering these two star carbon atom, this is the backside carbon, this is the front side carbon atom. Now let's draw this way. I am drawing here staggered form of Newman projection. So by considering here OH group, hydroxy group, these two is hydrogen atom. You can draw by yourself also for your practice. And now opposite to OH here NH group. I have already told you how to draw these structures. So you have to look from this side. This is on plane. Back side is hydrogen and front side is also hydrogen. So if you look this way, this OH is downside. So we have taken this side. Then H and H. Now look at this carbon atom. Here NH group is upside. So we are drawing here upside. From this way we are looking here. From this way. Okay. Then hydrogen. Then again hydrogen. So this is the staggered form of this molecule. Now we have to draw all the possible conformations. What will be the different conformation for this one? Eclipse is possible. How we can get different conformation? By rotating one carbon by 60 degree. Dihedral angle would be 60 between the two carbon atoms, between the two planes, dihedral angle. So I will rotate the backside carbon atom by 60. You can rotate the front one also. The result will be same. Okay. Here is OH, H, H, and H2. This is the same structure I have drawn before. Just I am drawing again for your better understanding. Yeah. Now we have to rotate the back carbon by 60. That is the dihedral angle. First of all, the front carbon will remain as it is. It was present before. Okay, and this carbon is moved by 60 degree. So we'll get here, here, here. So here is NH2. NH2. Then again rotate this by 60 degree. 60 degree. What you will get? Any idea? You have to make one carbon as it is, and then you have to draw the back side one. Again we are moving this carbon by 60 degree. Here, back side carbon. Then front one will remain as it is. Then back side one, back side one. Here, NH2. Again we got staggered conformation. Again we got staggered, then again we will rotate it by 60 degree. 60 degree. What will happen? We will get eclipse conformation. That means the dihedral angle between the two plane will be 0. In staggered conformation, the dihedral plane is 60, and in eclipse form it is 0. So I am drawing a here eclipse form. It is not there is no distance between these two bonds. I am showing here because it is overlapping one above the other. That's why I am showing this way. But this is not the bond distance. So this is 0 degree angle. The one bond is behind the other one. That's why I am showing this way. So this is again the eclipse form. We will show them. Again we will rotate it by 60 degree. Okay. Then what we will get? OH. By keeping one carbon at this own position, we are rotating the backside carbon atom. So here we got again the staggered conformation. Then we will rotate it by 60. Again 60. What I will get? This is our OH. Sorry, this will we will get eclipse here because from staggered to eclipse we will get by 60-degree rotation. So here I will draw the eclipse one. One carbon will remain as it is. The other one I will draw here. This is OH. Then H. NH2 will come here. And again OH. Sorry, H. Now we will again rotate this configuration by 60-degree, and we will get this one again our starting one. Okay, so these are the conformations possible for this molecule. So and now we have to find out the energy of these conformations, so which will have higher energy and lower energy. So you can see here in staggered form the dihedral angle is 60, and they are apart from each other. That means there is less repulsion between the two bonds and two molecules. That means staggered form is more stable compared to the eclipse one, because eclipse one have 0-degree dihedral angle and staggered form have 60-degree dihedral angle. That means staggered one will be more stable, right? Now we have to find out which staggered is more stable and which eclipse is least stable. Now you can see how many staggered conformation we have in this molecule. This is 1, this one is the 2, and here it is 3. So in these 3 conformation, you can see here in 1 we have NH2 and OH group apart from each other by 180-degree. 180-degree. That means there is less repulsion between the lone pairs and bond pairs of these functional group. That's why this configuration will become more stable, and this is called as anti because OH and NH2 group are anti to each other. That's why it is called as anti. And here there is no repulsion. There is not much that repulsion compared to the other conformation. That's why it is the most stable, because hydrogen is very small and NH2 and OH are far from each other. Okay, now we have to find out the second one. Here you can see here second one. Okay, in this second one you can see the molecule have two functional group each which are separated by 60-degree. OH and NH2 have 60-degree difference here, unlikely compared to the first one which has 180-degree separation. So here it is they are separated by 60-degree, but still stable because it is have 60-degree dihedral angle which is not in eclipse one. So this is the second stable compound. Now you can compare the second and third, right? The second and third are both same. Both are same, just the uh, NH2 is left side here, and in that conformation it is right side. So both are same. So these conformation are called as Gauss interaction. This is a Gauss interaction in which two functional group are interacted by 60-degree angle. It's called Gauss interaction. Both are Gauss. Okay, now we will discuss the eclipse one. In eclipse one, you can see this is the 1, 2, and 3. In these 3 eclipse conformation, you can see here in first one, the hydroxy group and amine group are separated by 60 degrees. So there is a dihedral angle is 60, and here torsional strain is also there. So you can see here hydrogen and NH2 are the NH2 are in same plane, and they have bond pair repulsion, and the energy will become higher compared to the anti one. So this molecule have higher energy, but if we will compare to the other eclipse form, we will see here OH and OH-NH2, sorry, hydroxy and amine group are one above the other. So here the repulsion is more compared to the first eclipse form. So because NH2 and OH have lone pairs, and lone pair repulsion and angle strain are high here, so that means the stability will become low, energy will become high, and stability will become low. Higher the energy, lower the stability. So this will become less stable, because NH2 group and OH group have bond pair repulsion, and lone pair repulsion as well. Now we will see the third one. Third one have again third one is similar to the first one. So 1 and 3 have same energy. Second one have the highest energy. And if we will talk about the staggered one, then staggered one have the high energy, low energy, and 2 and 3 have the same energy. Now we will give numbering A, B, C, D to draw in the energy profile diagram. So I will erase the first this numbering. So this is the A, B, C, D, E, F. Now we will write here the stability wise order. Which one was the most stable? A, right? A is anti-conformation and is more stable. Then after A, which will be more stable? Gauge interaction. Gauge form of this molecule is C and E. Both are same. C, E, same. Then eclipse form. Which eclipse form will be more stable? B and F. B and F are same, and D have high energy. B equal to A, and least stable one is D. Okay. Now remember this one. Now I am going to draw the energy profile diagram. These conformations we have discussed earlier in previous class. So practice yourself to get more understanding. Okay. So this is the graph I'm drawing here. Here energy on y-axis, energy in kilocalorie you can see. Okay. Here is rotation. On y-axis we have, on x-axis we have rotation. So first is 0, sorry, 0 is here, 0, then 60 degree, please mute yourself. Okay, then 60 degree, then 120. We are rotating by 60 degree. So we will get this way, 240, 300, and 360 will be same as 01 because it will rotated by completely 360 degree. It will become same. Now as I have discussed, I was rotating one carbon and we got this way result. So now I will write here A was for, we were getting A by rotating the molecule by 60 degree. So I will write here A. The A was staggered one, right? So the energy will be low. Staggered one have the low energy, uh, and it was the anti-conformation. That's why I'm drawing here. Okay. It was at 0 degree. Now by rotating the 60 degree, we got the eclipse conformation, which has a high energy compared to the staggered one. So the B molecule was having a higher energy compared to the staggered one. So B here. Then again we rotate that molecule by 60 degree and we got what? C. C was the staggered one, as I have discussed earlier. So staggered one was coming here. Here. Then again, after getting the C, I will write here A, B, C, then D. D was the least stable one. So it will have high energy because hydroxy group and amine group were repelling each other, because the dihedral between these two functional group was 0. That's why it has high energy. So here we have D. The recording will be available on YouTube. You can see from starting, because those who are joining now, it will become difficult to understand this one. Then again 60 degree from eclipse to staggered one. Then we will get E. E have same energy as C has. Then again it will be rotated by 60 and we will get the F. F is the eclipse form. So we will get energy here, F. And after rotating the 60 degree of the F eclipse conformation, we will get the starting one as it was, A again, A. So we will draw this way, energy is going this way. This is the energy profile diagram of this molecule by considering the C-C bond as the axis of molecule. I hope all of you understood this one. Let's move to the next slide. So next slide is basically talking about the configuration and conformation. So before solving the second question, this one, stability of the conformation, I would like to give a brief introduction about the configuration and conformation. So what is configuration? Configuration is nothing but the relative position of the atoms present in a molecule are changed by cleaving uh, and forming a new chemical bond. That means if we have suppose two molecules, from one configuration to other configuration, we can change by breaking or cleaving the bond, and not by rotating. That is called the configuration. Two configuration are not interchangeable without cleaving the bond, but in conformation, the two molecules are the same as one other, same molecules, and the conformation can be changed by rotation of single bond. You can see here in these two images different configuration. What is the difference between the first two dogs? Can you see here? If you see here the tail is there, and here we have this. It's not the, it's just for understanding. uh, See here, and tail is here. So are these two molecules are same? Suppose this dog is molecule, these two are same? No, right? The bond position, or we can say the tail and foot position, leg position is different. So these are the different configuration. These are not interchangeable. But in this case, if you will see, this is the conformation. So are they same? The both the molecules are same? Yes, the both are the same, but only representation mode is different. Here it is dog is standing, here it's jumping, but all the positions and bonds are same. But in this case it is not same. So this is the confirmation. That means everything will be same, the bond and angle, everything would be same. The only difference will be the rotation of single bond around the axis, and it do not involve the bond breaking and bond making. Now we will discuss the different types of strain present in the molecule. So there are three types of strain is possible. The first one is the torsional strain, then the second one is steric strain, and the angle strain. So torsional strain is nothing but the extra energy of eclipse conformation. As I told you, eclipse conformation have one bond above the other one. That means the dihedral angle between the two bonds is zero. So that's why the extra energy of eclipse conformation arising due to the repulsion between the bonding electrons of one substituent with the other one, because they are close to each other. Now the second one is the steric strain. Steric strain is nothing but the strain induced uh, uh, due to the repulsion between the electron cloud and interacting atoms. How we are getting strain? When two atoms or two groups are in a molecule are too close to each other, and they are repelling each other. That time we observe the steric strain. The third one is the angle strain. An angle strain is induced in a molecule when the bond angle are different from the desired tetrahedral angle. The desired tetrahedral bond angle is 109. If we are getting the angle less than this one, that means there is the angle strain. So because of some configuration, sometime we observe this strain. So we will discuss here. Now because mainly we are talking about in this live session about the chair confirmation, cyclohexane, not the chair confirmation, cyclohexane. So we will discuss cyclohexane before starting the question answer solution. So both angle and torsional strain can be avoided by ring puckering. What is ring puckering? This is the structure of planar cyclohexane, and the angle you can see here is 120 degree. If you will see here, angle is 120 degree between the two carbon atoms, right? And here 12 eclipsing carbon hydrogen atom are there. That means here we can observe the strain. Hydrogen atom had the strain. Now to avoid these two strains, the first one is a bond. First one is the angle strain, and then torsional strain. Torsional strain by overlapping these two hydrogens. We can uh, we can do the ring puckering to avoid these type of strains. So here when we draw it in chair form, we can see here the bond angle is big, is now more than the previous one. Sorry, not here. So the angle strain is reduced here. You can say the angle is become 109 here, and this is the angle between two carbon is 1.4, which was not in previous case, which was missing one in previous case, because in that case it was more than 109. So compared to 109, 111 is closer compared to the 120, right? Compared to the 120, that's why 120 was one was uh, having more strain, more angle strain. So here angle strain is minimizes, and then the second factor is uh, torsional strain. So here you can see the hydrogen hydrogen interaction is also reduced, so that means torsional strain is also minimized here. We can avoid these two strains. This is the 3D image of cyclohexane after ring puckering. Now let's discuss about the energy and stability of these puckering chair conformations, chair and board conformations. Now we can see here chair have least energy. Uh, Least energy means more stability. When you draw chair, you can see all the atoms are separated each other by without by having without angle strain, without torsional strain, and there is a minimum steric hindrance also. When we will convert this chair to the half chair conformation. You will see here what is half chair conformation. See, I am drawing here. Sorry, half chair means half cyclohexane will be planar and half will be in chair conformation. This is the half conformation. Then no, this is half chair and half chair conformation. So these three atoms are in plane, and these three are in chair form. Okay. So here you can see in this half chair conformation, angle strain is there. Here 120 angle, right? And uh, hydrogen eclipsing is also there. So static hindrance is present here, or we can say torsional strain also. Torsional strain is also here. Static hindrance is also there. That means the energy will be higher compared to the chair conformation because of these three strain factors. Strain leads to the increase in the energy of the conformation. So half chair have high energy compared to the chair one. It's 10.8 kilocalorie per mole energy required to convert from chair to half chair conformation. The difference between these two conformation is 10.8 kilocalorie. Now we will see the board conformation. Twist board, not board. So before going to the board conformation, I will draw here twist board conformation. Sorry. This is the twist boat conformation. So here you can see the energy will be less compared to the half chair, because here the angle strain is not that much compared to the half chair. Here the in half chair we have observed 120-degree angle between the two carbons, but in this twist boat it is not there. So that's why it is stable compared to the half chair, stable one compared to the half chair. And these two carbon have, because it's a twist boat, yeah, these two hydrogens are also not having interaction. That's why we have less steric hindrance and torsal strain. Steric strain and torsal strain is low here. Now let's talk about the boat form. Okay, this is a boat form. Here, because of flag-pole interaction, if you will draw the Newman projection of this boat form, you will see the you will see the torsional strain, because it's a eclipse form of cyclohexane. Eclipse chair is a staggered form. In previous lecture, I have discussed this one. Because of flag-pole interaction, the energy will become higher compared to the twist boat. So that's why there is a difference in energy between the twist boat and boat conformation is there, and it is 1.4 kilocalorie energy difference is there. Boat is less stable compared to the twist boat. Now again we will see the other conformation, that is twist boat. Again why we are going this way, because from chair to half chair is convertible, then half chair to twist boat. Like in previous case we were rotating the carbon atom by 60, same here we can convert one conformation to the second one by uh, uh, rotational of the bond rotation of the bond present in cyclohexane. Now from boat to twist boat we can convert by rotation of the bond. Again we will get this intermediate, which is stable compared to the boat one. Then again half chair, then we will get chair conformation. Okay. By rotation of 60-60 we are getting these different conformations. So after rotation of 360 we will again get the chair conformation. So the most stable conformation of cyclohexane is chair, and the least stable is half chair. Boat and twist boat are stable, but not as much as chair one. They have a little bit high energy. Okay. Now let's start solving the questions. This is the first question. In this question, we have to find out the most stable conformation and why we have to discuss here. So you can see here, this is the 1,2-dibromo cyclohexane, and it is a trans form. Why it is trans? Because these two bromine are present on axial. If you will draw in planar form, you will see here. If you are not understanding anything, you can ask me in between. This is above the plane. This is below the plane. So this is the trans form of 1,2-dibromocyclohexane. So when you will draw in chair form, you will see here axial equatorial position. So these are two on axial position. That's why it's trans. And here also these are equatorial position. That means it is a trans form. So this is a trans form. If you are not getting how we can distinguish between the cis and trans conformation of cyclohexane, then you can let me know. I will discuss this topic in detail. Okay. For for this question now, we will consider trans here. Then we will draw Newman projection here. If we will draw the Newman projection of these two carbons, these two carbon, you will see these are anti to each other, anti to each other. I will draw here, right? So here bromine, hydrogen, and here it is methylene, which is connected to other atom. Methylene I am writing here. H, bromine, and sorry, methylene again. Okay, so you can see here, bromine and methylene have interaction. Here you can see here. So there is a strain here. Uh, this is called the 1,3 diaxial interaction. If you will see here, 1,3 diaxial interaction is here, present here. When we will draw Newman for this one, or we will see this here, there is no 1,3 diaxial interaction, but when we will draw the conformation in Newman form, you will see here we have bromine here and here, right? Because these are two bigger molecule and they are apart, separated by 60 degree dihedral angle, they will create repulsion, and the repulsion between them will be high compared to the 1,3 diaxial interaction. Compared to the 1,3 diaxial interaction, the repulsion between these two bromine atom will be high. That's why it will have high energy compared to the first one. Compared to this one, because here bromine are apart from each other by 180 degree dihedral angle, but in this case they are apart from one apart from 60 degree dihedral angle. So that's why this conformation will be more stable compared to the first one. Now let's talk about this configuration. In this case, you can see this is the axial third butoxy group, and here is equatorial. So in case of axial, you can see here we will observe here 1,3 diaxial interaction. If you will open this and draw it here like this way, sorry, here CH3, CH3 and CH3. So you can see here this CH3 is close to this hydrogen. So here we can see a 1 3, here Gauss interaction will take place. 1 2 3 4. I will show here the Gauss interaction. If you will draw the Newman projection for this carbon and this carbon, you will observe the Gauss interaction. Gauss interaction means the dihedral is 60 degree. So I will draw here first. This carbon, and the below carbon is here. CH3, CH3. Okay. Then here two methylene groups are there. This is proton. So you can see here we have here 1 4 Gauss interaction. 1 4 Gauss interaction. 1 2 3 4. So because of this Gauss interaction, the strain will be higher here and the energy will increase. Now we can compare here a 1,3 diaxial interaction also. That's why the stability will become less and energy will become high. For 1,3 diaxial interaction, the value is 1.9 kilocalorie. Now in case of this axial turbidoxy group, you can see this is the turbidoxy group. In next lecture, I will discuss detailed energy of this conformation. Then it will be better to understanding. Here we have not observed 1,3 diaxial interaction, but only the Gauss interaction between the CH3 and methylene group. 1, 2, 3, 4. This carbon and this CH3 have Gauss interaction. Gauss interaction between these two groups. And here 1,3 diaxial interaction is not there. That's why the energy is less compared to the axial turbidoxy group. How we can compare? You can draw this carbon and this carbon on Newman projection. 1, 2. Then you will get this CH3 and this methylene are separated by 60-degree dihedral angle, and that is a that is called the 1,4 Gauss interaction. That is nothing but the Gauss conformation of these two carbons Newman projection. So here the strain is less compared to the first one, because here we have the 1,4 Gauss interaction as well as the 1,3 diaxial interaction. 1,3 diaxial interaction with this carbon, tertiary carbon, and this hydrogen, this methylene hydrogen, and Gauss interaction with this one. Here any other Gauss interaction is possible. Yeah, you can draw these two carbon, and you will observe that uh, in this case, if you will draw these two carbon, here one and here, because there is no other substituent is present on this ring, there is all are hydrogens and the other strains are not possible. So only 1,3 diaxial interaction and Gauss 1,4 Gauss interaction is possible. So the energy of the axial will be axial turbidoxy group cyclohexane is higher compared to the equatorial, because here we have only one type of strain. Okay, now let's talk about the cis and boat and chair conformation. So before discussing that question, I would like to give the conformation of these boat and chair form. So here this is a chair form and this is the boat form, right? In chair form, you can see here we have axial equatorial bonds, right here. So now we are talking about these interaction, hydrogen hydrogen interaction. So you can see here there is not that much interaction of these two hydrogen as in case of the boat form. You can see here is flagpole interaction of hydrogen hydrogen is present. That's why the strain is more compared to the chair one, right? Yeah, you can see staggered form. This is the eclipse form of boat. So when you will draw the chair conformation of the when you will draw the Newman projection of this chair conformation by taking the two carbons, which two carbons? This on one Newman, and these two are in same plane from this side. I am talking about from this side. These two are in plane. 1, 2, and this is 3, 4 in plane. You will observe this configuration staggered form here. So this is the front carbon 2, this is the back 1, 2, the back one is 3 here, and this is the fourth one. Okay. So you will observe here the strain is less compared to the boat one. Why? Because here we uh, uh, we don't have torsional strain. Torsional strain means the dihedral angle between the two bonds or two groups is 60, but sorry, 0 is means torsional strain. So here you can say the both all the bonds are separated by 60 degree. But in both form, you can see here 0 degree dihedral angle is present. That means the torsional strain is present in both form, but not in the chair form, because chair is a staggered one, and staggered one is always more stable compared to the eclipse one. So because of this hydrogen-hydrogen interaction, this is a flagpole interaction, as I have discussed here. Here, 2.9 kilocalorie energy will increase in both form because of this interaction. But if this flagpole interaction is not present in chair form. You can see in chair form, the two hydrogens are apart from each other, far from each other. Now, the second reason for increase in energy is here. You can see here uh, the energy between the torsional strain is increased by 1.0 kilocalorie, which is again increasing the energy. Here two protons and this side two protons. That means 4. 1 into 4 energy will increase here. And now here this one is 2.9. That means total energy will become 6.9 kilocalorie compared to staggered form. So the energy difference between these two conformation is 6.9 kilocalorie. One from this hydrogen-hydrogen interaction, and one 2.9 from flagpole interaction. Okay. So I hope all of you got this one. So in these two, which one will be stable? Chair one. Chair conformation is more stable compared to boat one. Okay. Now let's move to the second question. Uh, Classify the following molecule as a chiral or achiral. So for chiral or achiral molecule, you have to understand the basic phenomenon behind this term. So what is a chiral molecule? The chiral molecule which has no symmetry element present in that molecule is called chiral molecule. Means no plane of symmetry, no center of symmetry or any other symmetry element. So these molecules are called as chiral molecule. Uh, and chiral molecule are able to rotate the plane polarized light into different direction. If the molecule is rotating the plane polarized light is right direction, that means it will become di- uh, dext, uh, dextro dextro rotatory, and it will rotate in uh, left direction, that means levorotatory. L, it is denoted by L. So D and L is nothing but the it depend on the rotation of plane polarized light in uh, different direction. Clockwise direction means D, anti-clockwise direction means L. And these plane polarized light can be only rotated by chiral molecules, not with a chiral. So we have to find out the chirality of the molecule by passing some symmetry element through the molecule. Then we will see which symmetry is present and molecule is chiral or not. So the first example is cis 1,2 dichloro pentane cyclopentane. So here we can see cyclopentane. So here we can see we have two chlorine group above the plane. When we will pass the plane from here, we will see these two are indistinguishable images of each other. Indistinguishable mirror images. Okay. So these are separate, these are mirror images of each other, and these are the plane of symmetry is present. That means if plane of symmetry is present, that means the molecule is achiral. This molecule is achiral. As I told you, there should uh, the symmetry element should not be present in chiral molecule. That's why we are labeling this molecule as a achiral, because plane of symmetry is present. Okay. Huh. Ne the next one is trans 1,2-dichlorocyclopentane. So in this molecule, now again we have to check the symmetry element. See here, if I will pass the plane here, I will not get the same uh, confirmation or same image other side. Here left hand side is not equal to the right hand side. You can see left side we have a chlorine group above the plane, and left side it is below the plane. So that means there is no plane of symmetry present here. Okay, there is no plane. Sigma plane is not there. Now we will cut past the horizontal plane. We have discussed the symmetry elements in a previous lecture, last lecture. So you can go and watch that lecture to understand this one, how we are passing plane. So this is the horizontal plane. If we will pass here, so we will not get the two equal halves, because the this upside fluorine will not give the exact transformation from below the plane. So this is that means here sigma h is also absent, horizontal plane, and sigma b is also absent. Now let's talk about the different symmetry. So here can we rotate this molecule by 180 degree? I will rub it. Okay. Now we will pass the axis here. If we will rotate the molecule by 180 degree, we will get the same configuration as this molecule has. That means here the axis of symmetry is present, but the axis of symmetry we should avoid only the plane of symmetry. Axis of symmetry means doesn't mean it's the achiral. So here plane of symmetry is not there. Only the axis of symmetry is there. That means this molecule is chiral. Only the axis of symmetry should be present in chiral molecule, not the other symmetry elements. So this molecule is chiral. Now let's talk about this 2,3-dichlorobutane. 2,3-dichlorobutane. So here you can see this chlorine is above the plane, and this is below the plane. We have to check the symmetry element present here. So when we will pass the plane from these two carbon here, this is a vertical plane. So uh, you will not get the same molecule we have one right hand side to the left hand side. So that means here sigma plane is absent, sigma b. Now we will cut the molecule, sorry, when we will pass the plane here, we will observe that again this plane is not giving the same configuration compared to the previous one. That means this plane is also absent. So the plane of symmetry is absent in this case because we are not getting the indistinguishable mirror images after passing the plane. That means sigma plane is absent in this molecule. Plane is not present. Okay, plane of symmetry is not present. Then we will see the axis of rotation here. Here, at the, here if we will pass the axis from here, and if we will rotate this molecule by 180, 180, we will see this chlorine atom will come this side, front side, and this will go the back side. That means this is the actual indistinguishable image we are getting after rotation of 180 degree. That means the uh, uh, axis of symmetry is present here. Axis of rotation axis is present in this molecule. That means it is a chiral. Only the C2 axis is present. Axis of rotation. That means it is a chiral molecule. Okay. Now this is the other another case. One 2,3 cis 2,3 dichlorobutane. So here you will see both the chlorine atoms are above the plane. So when you will pass the plane from here, you will see the both the right hand side and left hand side are same. You can see this way. So both the structures are same. Imagine in 3D, this is front side, this is front side, these are two, sorry, sorry for the confusion. Actually this is drawn in zigzag form, so I will write in first simplest form, then it will become easy to understand. If we will rotate this carbon carbon bond, you will observe here both the chlorine atoms are in same plane here, same plane. Sorry for the confusion, this is the trans one because this is the zigzag form. So if you will write in Fisher conformation, Fisher form, you will see here these two are CH3 group, CH3 and CH3, these two groups. Okay, and in Fisher conformation, these two upside and downside bond are below the plane. We are considering below the plane this way. I will write here, this is above the plane, this is above the plane, this is above, and this is below the plane, these two here. So these CH3s are below the plane on same side and same side. That's why I have written here on same side. Okay, if you will rotate this bond by 180, you will see both the chlorines are on same side, on same side. Okay, so when we will pass the plane here, we will see the right hand side and left hand side both are equal and same. That means we are getting the indistinguishable mirror image by patching the plane of symmetry. So that means here plane of symmetry is present. Plane of symmetry is present. And now because any plane is present, that means the molecule will become achiral. So this is the achiral one. This molecule is achiral because plane of symmetry is present. Okay, you can pass plane here also. You can see, right? So this is the achiral. Now this 2,3 cis dichlorobutane have different conformation if we will draw it in Fischer conformation, Fischer form. So I will write this way also and Fischer also. Chlorine, chlorine, CH3, CH3. Okay. Now let's write down in Fischer form. So both the chlorine are opposite side. Here hydrogen, hydrogen, CH3. Okay, now we have to check any plane of symmetry is present or not. So here you can say if we will pass the plane here, we will not get the mirror image of this one because this chlorine is in front side and this is the back side. That means both are different. So we will not get uh, the same image, same configuration by passing the vertical plane. Now let's check the horizontal plane. So if we will pass the horizontal plane from here, we will not get the same image because this CH3 is downside, these two CH3. But if we will pass the plane by cutting the two chlorine molecule, we will not get the same configuration because these CH3 will become upside if we will pass the plane. So again, the sigma H is also absent, sigma V is also absent. You can check here also. We cannot pass plane through here and here also. In this way also we cannot pass plane, right? Okay, now we will check the center of sorry, axis of rotation here. uh, is there any axis of rotation present here? Axis of rotation, symmetry axis. Yeah, you can see here, if I will pass the rotation axis through here and I will rotate the molecule by 180 degree, C2 axis 180 degree, you will see this this chlorine will come this side, back side, and this will come to front side because I am rotating uh, on this axis rotation. So by passing C2 axis, we will get the indistinguishable molecule compared to the starting one. Not identical but indistinguishable. That means here axis of rotation is present. C2 axis of symmetry is present. Because the symmetry axis is present only and sigma planes are absent here, the molecule will become chiral. The molecule will become chiral here. Okay. I hope all of you understood till here. If uh, if any doubt, any question regarding these questions are there, you can ask me in next live session, and I would like to solve all your doubts and problems. And if any confusion, any improvement is required, please let me know. Thank you all of you.